Okay, good afternoon. Yes, I'm on. So this is continuing with the W-first theme a little bit, although it's a bit of a cheat. This is really more of a UCURT talk since we don't have W-first data in hand to test, but we're doing what we can to use other data as a pathfinder. So this is work with a couple of staff at JPL from the machine learning group, Carrie and Selena, along with the UCURT team led by Yossi. So the idea here is twofold. First off, we just want to try and make things easier on ourselves as far as the traditional way of doing some by eye analysis to identify some of these events. And we want to save the work and have the computer do as much as it can without humans in the loop. And then on top of that, we want to have some consistency in this detection as well. And I mean, I certainly find myself that when I'm going through 1,000 events, by the time I get to the end, I'm a lot more liberal in my selection of events. Yeah, sure. And whereas a computer will do this in a robust way every time. As I said, we're going towards UCURT with two goals. Again, saving time and statistics. We need this for the statistics. I was going to put in a slide on the history here, but I left it out because there's just too much. I mean, as far as just event selection in general, not machine learning, there's countless number of papers. I was going to have you raise your hand if you've worked on this, but it's probably easier to not raise your hand if you've worked on event selection. Machine learning, on the other hand, again, there's decades of work in astrophysics applications, and in particular recently with light curves. There's a lot of papers on Kepler identification of transiting events, but the only paper I know with the combination of the two, so event selection and machine learning, is Łukasz Wyrzykowski's paper from a couple years ago on OGLE, and this is very comparable to what he's done. As a reminder, the UCURT survey is 2/3 through its main survey. We've got our last season this year. It's a survey really getting into, it's a near-infrared microlensing survey, so we're really getting in right into the center of the galaxy. But it's relatively small. It's from Hawaii, so we only have a couple hours a night to observe the bulge. And just a few nights, few epochs per night over maybe 4 months. Okay, so for the machine learning, I'm sure most of you are, some of you at least, are not familiar with this. The basic steps are, first off, creating a training set. And so unfortunately, we can't entirely remove the by eye process from this. We have to still go through and tell the machine, define somehow each of the classes that we're interested in. And we've done this the same way as everyone else. And we find, let me get the pointer out, hundreds of events over the last few years. We had a couple of test seasons before we get into our main survey. I'm just going to be focusing on last year's data for the rest of the talk, where we've got about 200 events. Second step is in defining so-called features, so reducing each light curve to some characteristic set of simplified numbers. This is the exact same thing you do even without machine learning. You want to take the dispersion of light curve, how many points above the baseline, the dispersion of the baseline. The difference here, just to simplify machine learning, is that rather than making some strict cut, okay, you want X number of points above threshold for baseline, you make it more fuzzy. You have some kind of defined classifier that groups things in your n-dimensional space, and in this case being maybe 50 or 60 different features that you throw in. The particular classifier that we use actually is very useful in this regard, that you don't have to pre-select the features. You can just throw everything in and let it figure out which ones are most useful in defining classes. So again, there's this classifier. This is the third and last step, is in picking this classifier. We're using what's considered the standard random forest algorithm. There are lots of other choices. We haven't seen any improvement with some. Some methods are a lot slower, Gaussian processes, for example. But just to give you a flavor for how this might work, so this is our 2017 data set with just two features, one being the chi-squared for how well it's fit by a microlensing curve, single source, single lens, and then how well it's fit by a sinusoid. And so this is kind of our data set grouped by blue microlensing, red other variables. And three of these different classifiers, I mean, there's no correct way to group these. It's a messy, complicated space, even in 2D, let alone when you consider all the other features. You can see, yeah, of course, there's more blue here and red, but there's a few points. And so it's not clear which of these is better? Nearest neighbors is the most intuitive. You just group by how close it is. Random forest is kind of the next most intuitive. It's based on decision trees, where you decide, and for each variable you do make cuts actually. Yes, no for each one, but then you group into the trees and a forest of trees. So you do see sharp cuts in here and how it's defining things. This sport vector machine is the one I know the least about. I thought this would be the best performing because it's the most sophisticated. It's a little more complicated, but in practice, it's no better. Okay. So goal number one was, again, to see how well we do compared to this by selection. And again, we found 177 events. The result, I'm a little reluctant to go to the next slide because it's not great. So this is the standard delta chi-squared cut that's used to say how significant, how microlensing an event is. And we were looking at everything below 500 before, and now going deep down into the junk curves. So now, rather than looking at thousands of curves, we're considering hundreds of thousands of light curves with the machine learning. And we only get tens more events. Not great. As opposed to, back in Wukisch's paper, he was able to find 1,000 events that had not been detected by the early warning system. That's a little different, though, because he wasn't using the exact same data set. There's some caveats, but still, it was a little disappointing. Now, meanwhile, we miss a few events, so we're a little below the curve. That's expected, of course. It's not going to be perfect. And meanwhile, this dashed line is how many it detects that are, there's some false events in here. So again, we've got some false detections. This is not good. We want to be as precise as possible, which is defined based on these false detections. But still, it's again, very different than Wukisch's paper, where they had 1,000 EWS detections that they didn't find. So quite different. Meanwhile, note, though, that there is some flexibility in how you define these detections, actually. Each curve is given a probability that it's microlensing or not. And the normal thing to do is if it's 50-50, if it's more than 50% microlensing, yeah, go for it. That's microlensing. But you can set that threshold wherever you want. So you can make a more conservative threshold, this blue line, where you really limit the number of false detections at the expense of missing, again, a few real events. Or you can be very liberal. If your goal is simply to just limit your space from hundreds of thousands of curves down to a few thousand, just to help you with the by eye even, this is a useful thing to do. Okay. Now going to goal number 3, statistics. So just from by eye, you can't do statistics. You don't really know how many you've left out. You do need to have some sort of well-defined selection criteria, as several authors have done. But again, as I said, the difference is strict cuts, deterministic, versus this more nebulous classifier. And in both of those cases, you have to calculate, of course, detection efficiency, which Savannah, who's here, has a poster. You can talk to her for more details, but she's been working on injecting events into the image frames and really doing this the proper way. Meanwhile, this is not complete yet, but meanwhile, we're just doing ejecting events right into the light curves to get detection efficiency. This is great, as opposed to goal 1, where we didn't find too many new events. This is as good as we could have hoped for. We're getting up to even 60% detection efficiency at our sweet spot of tens of days events. It improves some from 2017 versus when we add in 2018 for baseline. Because remember, we only have 100 some days. We don't have baseline. We don't have a 25-year program for this data. It's quite limited. But with the baseline, even so, here we're getting into quite good results. As opposed to, let's compare this back to the non-machine learning curve. So this is really the key slide of this whole talk, that detection efficiency can be quite low if you're very conservative. I mean, the goal of this paper was not to have a high efficiency. The goal was to find short period events, and in a very conservative fashion, very reliable. And so rather than a 20% detection efficiency, we're getting up much higher, which is key for a statistical mission like WFIRST. You want to have as many events in there as possible, of course. Just as a last application that we've considered, last couple slides, I mean, as an application, is one criticism that's come up with this is that since we are in some sense defining our just on single len events as our main target, there's a criticism that maybe we're missing binaries, and certainly with some previous efforts that was intentional even to leave them out. So we went through and did the same detection efficiency on a range of binary curves up to a mass ratio of 10. And this worked pretty well. So we had about constant detection efficiency, 45% from Jupiter, well, Jupiter-like up to mass ratio 10 minus 2, but then for the high mass ratio, it did start getting lower by about 10%. But that's not bad at all. And more importantly, it's something that we can quantify as would be necessary for WFIRST. This is the end. That for the first goal, modest improvement in the number of events. It certainly can save a lot of time, though. It really depends on how much time you want to put into the BI. For our particular data set, varies from one to another, OGO versus UCART. For our data set, we really put in a lot of effort into the BI. We found all the easy ones, well, all the prominent high signal and noise events, and that was about it. Certainly, as you go to larger and larger data sets, it becomes more of an issue. Much more importantly, though, is the statistics. And whereas back, again, with the SUMI results, where there's less than half of the known events were included in the sample, a lot were thrown out, we no longer are throwing out many at all, just a few percent. And so I'm concluding from this that there really is potential here for machine learning to help with the bottom line requirements for WFIRST. Thanks.
Training set like for the various machine learning methods? Is it only like using mock data or also real data? And also, have you tried methods which don't use features, such as convolutional nets?
So the training set is the by eye sample, where we went through with several team members and cross-checked against each other. So we've tried to be as robust as possible there, but it still involves some opinions, let's say. And we used a series of classes, but we're mainly interested in microlensing, not microlensing. As far as other classifiers, we have looked at, let's say, outlier detection. We've tried a multi-level regular classification. We've done some active learning, particularly in a stage 1 approach. We've not gotten into deep learning neural nets. We're thinking about it. Like I said, we've got 2 experts on the team, so we might move in that direction.
Dave?
So one thing you didn't mention was how you selected the stars. And this is I think probably because you selected the stars in like a DUFOT or some kind of PSF fitting photometry of a static image rather than selecting stars when you see them vary in a difference image. And this makes a pretty big difference in the number of events you can find. If you detect them in a difference image, you get a factor of 1.5 or 2 times more events. It also makes a difference in your, how you compute the detection efficiency, because when you do it in a difference image, then the number of stars that you're sampling is somewhat arbitrary, because you need to set it like a magnitude threshold. It's not just the number of stars that you've identified. So in your comparison between to the MOA analysis, that is based on some random set of a threshold for the stars that are counted in the MOA sample. And then also this number here, the 474 out of 1,000, that's a cut based on how well the parameters of the event are characterized, not just how well they're.
Yeah.
Some of them, particularly the faint ones, have this blending degeneracy, and so you can't really use them very well in a TE distribution.
I really wanted to do a perfect apples to apples comparison against that analysis, but it was not possible for several reasons. Some you've outlined, and we're not doing difference imaging, and some we don't have as much baseline. There are a lot of reasons why I couldn't do the exact cuts.
Yeah.
So that's why I hope I was clear that that was an illustrative example, not an
Sure.
exact
Well,
comparison.
I mean, my main suggestion would be to try and detect the stars in the difference images, and you can probably find 50% more microlensing events that way.
Yeah, and I think Michael's volunteered to do this for us, right? Yeah.
Okay, let's thank Jeff. And our next speaker is Ruth Mary Clay from UCSC, and she's going to talk about planetary system architectures as probes of planet formation. But she's also going to talk for her student about effects of a phase of planet-planet impacts on the population of outer giant exoplanets.
Yes, one of my graduate students, Renata Froelich, was supposed to speak after me, but she unfortunately has a family emergency, so I'm going to be giving her talk as well. I think I'll just talk straight through both of them and take questions. I'm very happy to be here. I'm a theorist working on how planetary systems form and evolve, and I'm really excited about WFIRST and its prospects for teaching us about the outer regions of planetary systems. So one of the reasons that I'm here is that I want to learn about what you all expect from that data so that I understand appropriately how we should be making those predictions. So I'll be here today and tomorrow, and I'd love to talk with anyone about that while I'm here. Just one thing before I get started. As an outsider in this still relatively small field, listening to talks this morning, I'm really excited to see the junior people here who are bringing energy and ideas. I really encourage you to think about whether you are interacting with them in science discussions in as constructive a way as is possible. All right, okay, so I'm here to talk about planetary system architectures as probes of planet formation. And since microlensing really has its strength in statistics, I'll start with a couple of statistics that I find puzzling, and hopefully by the end of this talk you'll understand why I find them puzzling and what they might mean. So the first is that close-in super-Earths from Kepler appear to orbit about a third of Sun-like stars, and gas giants, in contrast, orbit something like a sixth of those stars, and those are from radial velocity systems. They're much further out typically. All right, so I find these numbers puzzling, and I'll tell you why. So first, I'm talking about planetary system architectures. I should define what I mean by that. So here's the architecture of the solar system, right? We have in the middle 4 rocky planets, which I've labeled here all as Earth, because of course that's as well as we can tell from any of our detection techniques. We have 2 gas giants, and then we have 2 ice giants, and a couple of belts. And as, of course, you know well in this room, Kepler probes in the tiny innermost region here, and radial velocities probe a little bit further out. But most of this parameter space, when plotted this way, remains unknown in other planetary systems. All right, so why does that matter? Let's just remind ourselves about how planetary systems form. Here's the famous Orion star-forming region. We see a bunch of baby stars in there with little disks forming around them. They collapse under their self-gravity because of angular momentum. They have to process some of that material through a disk. So you have gas and dust and ice in the outer regions of the disk. In the inner regions where it's hot, it just becomes gas and dust. And in that disk is where you form your planets. So within that disk, you start with tiny bits of dust, which here I've made as a cartoon as just little dots. And the key thing that I want to point out here just is 2 things. The first one is if you have more material, they can collide and grow faster. That's intuitive. And the second one is that the growth timescale increases as the orbital time increases. So your collisional growth processes all scale with your orbital timescale, and that, of course, gets longer as you go away from the star because of Kepler's third law. So if we put all this together, we can get a really nice picture of why the architecture of our solar system exists. Right? In the inner region, you just don't have very much stuff, so you make puny planets like Earth. As you go out farther, I've sort of colored it a lighter blue to show that you have ice. You also just have a much bigger area in this circle. So for both of those reasons, you have more material. You can make bigger solid things. And in fact, you can make big enough cores in principle that you can go run away and accrete a giant gas envelope. Then as you go farther and farther out, you have a longer orbital time. It takes longer for that to happen. You can still make those big cores, but by the time they've done that, there's not enough gas, and so they don't end up with a huge envelope. They can only accrete the small amount of remaining gas that was left. And of course, this picture worked very well when we were just trying to explain the solar system. It worked fantastically. But now that that we have exoplanets, it doesn't work quite as well. So I'd like to just explain this picture in a little bit more detail because it's going to become relevant later on. So bear with me for a moment and recall that the planet's gravity dominates within what's known as its Hill radius. This is where planetary gravity balances tidal acceleration. Within the Hill radius, you can have a moon that orbits stably around your planet. And within the Hill radius, in principle, if you're sitting in one of those disks, you can accrete all of that material that's orbiting with you around the star. And one of the main concepts that is employed in understanding that original solar system architecture is known as the isolation mass. This is the mass that you get to when you've accreted all of the material within your Hill radius, or really a few Hill radii, that's available for you to accrete. And if you don't have any way of replenishing that material, then once you've accreted it, you're done. It turns out that as you go more massive, your Hill radius gets larger, but not fast enough to allow you to not stop. You do end up stopping. You have an isolation mass. Okay, so if we go back to this picture, in the inner region, the idea here is that isolation masses are small. They're in fact smaller than the Earth, right? You have Mars E-mass isolation masses. And then in order to complete the growth of the rocky planets, there was a giant impact phase. That's why we have the moon. You had a big collision when the isolation masses destabilized and had a final phase of growth. Meanwhile, in the outer system, the isolation mass was just small enough that runaway gas accretion takes a long time. That allowed it to stick around for long enough without going runaway for the disk gas to dissipate. Okay, so now let's look at the exoplanet data. And of course, it doesn't fit in with this picture. So let's just recall a few of the key results that we have so far. From the radial velocity data, here this is semi-major axis and eccentricity, we have a ton of high eccentricity giant planets. We don't see that in the solar system. From the Kepler data, we see a ton of super-Earths or mini-Neptunes on very short period orbits. We don't see that in the solar system. And from the direct imaging data, we see wide separation giants. This is Neptune's orbital distance. These are 7-ish Jupiter mass planets at very wide orbital separations. So we don't see that in the solar system either. All right, so the data show that more must be going on than that initial formation picture that was made for the solar system. All right, so what more is going on? Probably a number of things, of course. But one of the main things that we've been talking about in recent years is the idea that gas drag causes drift, and that makes this idea of isolation suspect, right? So that solar system formation picture really depended on the idea of the isolation mass. But if your gas is causing the material to drift through the nebula as you're forming things, then maybe you're not isolated at all. So why does stuff drift? Well, let's imagine that you have a planetesimal that wants to orbit your star here at the Keplerian velocity. But the gas feels a radial pressure gradient outward. So it thinks it's orbiting a lower mass star than it's actually orbiting. So it's going a little bit slower. So this thing is plowing through the gas, and what that means is that it's losing angular momentum and falling in. So if you have a big object, then your surface area to mass ratio is small, so you have a small acceleration, you don't drift as much. If you have a small object, the opposite is true. So that's a little bit oversimplified. It turns out that if you're at an intermediate size range, about a meter size at 1 AU, then you get the most drift. Okay, so we can actually see this in the data. This is not just theoretical, it's actually going on. If you look at disks at various wavelengths, and this is a compilation from Sean Andrews. You can see that disks look smaller at larger wavelengths. So this is like a centimeter, a millimeter, a little bit less than a millimeter, 1.6 microns. And at these wavelengths, you're essentially seeing emission mostly from particles of about the size of the wavelength. So the bigger ones have drifted in more, the smaller ones have drifted in less, and that's what you expect in this size range. So larger particles are drifting in more and more quickly in this case, and you can actually see that in the data. So stuff is moving around, for sure. All right. Okay, so what can we do with this? I'd like to step back and take a bird's eye view for a moment. I'm going to defocus all of the complicated physics that we could put into this. And I'm going to start with a couple of assertions. I'm going to start with saying that the solar system exists, and it isn't a bizarre statistical fluke. I'm happy with the assumption that it exists. I'm just going to assume that it's not a fluke. I'm also going to assume that there are only a few controlling parameters that determine the diversity of outcomes of systems around different stars. A few need not be 1 or 2. It could be 7, it could be 10. Here's stellar mass, solid mass in the disk, accretion properties of the disk, neighboring stars. There are all sorts of things. But if you've worked on planet formation models, you know that no matter how many you add to this, it's still going to be a lot less than the number of knobs in the planet formation models. So there must be some reason why the solar system is not the same as those other systems that we've seen. So the question is, what is the reason, and can we get at it? So I'm gonna start with one of the most simple one. It doesn't have to be the one that matters, but we often assume it is, right? So even if we learn that it's not, we've learned something important. And that's the amount of solid mass in the disk, which maybe metallicity is a proxy for if you're looking at a sample of similar mass stars. All right. Okay. So I'm going to take a moment to explain my cartoon here. So what I'm trying to say here is, because I'm going to come back to this cartoon a couple times. So you have disk mass on this axis. There are no units. That's on purpose. I don't know that this is the right stretch for these different regimes. And here's distance from the star. Now, brown is rock, red is gas giant, blue is ice giant, and here's the solar system in the middle. We've got rocky planets, and then we have gas giant planets, and then we have ice giant planets. And the hypothesis on this plot, right, is that as you go up in mass, you get more massive rocks in here. It's easier to make your gas giants, and if you go up so high in mass, suddenly you end up with a dynamically mixed set of orbits. And I'll say why in just a moment why I think that might be true. And then as you go down in mass, maybe everything just gets smaller and smaller, but maybe also you could have drift of material inward, and you could end up with some things in the inside. All right, so why would we think that there are dynamically mixed orbits? Well, recall that one of the earliest results in exoplanet science was that the frequency of hot Jupiters increases with stellar metallicity. And I'd like to put that result on a different plot here. This is semi-major axis, and this is mass of the planet. So up here are the giants, and this is all radial velocity data. Red means that this is metallicity that is less than solar. If you look up at the giants up here, I want you to notice that they're all out here. They're all out past 1 AU, except for a few stragglers. All right, woo. And then if we put up the higher metallicity stars, though, that's not true at all. They've smeared out into the interior. So if you look at them together, first of all, this is where those early results were coming from. Yes, higher metallicity stars have more planets, but it's not more any sort of planets. It's more gas giants in the inner regions sorts of planets. And it really looks like maybe you do form those giants mostly out here, but in the high metallicity systems, they've been smeared out, possibly by dynamical interactions with each other. So that's where that idea comes from. Maybe if you have a really high metallicity system, you're more likely to have another giant nearby or multiple giants nearby that are able to dynamically mix you into this region. All right. So that's the hypothesis up there. So basically I'm saying, oh, all of the RV systems that we've seen minus epsilon are in the top of this plot here, right? But we're not. We don't look like those systems. Maybe if we want to look at systems like ours, we want to look at lower metallicity systems, not at the ones that had the high metallicity or we thought most planets were. Okay, here's another thing that we could do with this plot. We could say, all right, well, what about those super Earths? Could they be the more massive, the more metal-rich systems, in which case they should have giants out here? Or instead, you could imagine that they're the ones where giant formation failed, right? You made Neptunes out here and they never actually got to be giants and they migrated in. Or your giants stopped your dust from drifting in. Whew. And in these systems, the dust all drifted into the interior and turned into the super Earths. People have made models of both sorts, and they're both, compelling. Okay. All right, so now I'm going to come back to my question. Why are super Earths more common than gas giants, which are found around 1/6 of stars? Why was the solar system able to form gas giants but not super Earths? Well, maybe it's actually evidence for this, right? If there are more of these than there are of these, but we have these and we don't have those, then how can the super Earths be a population up here? Instead, maybe this is what's going on: migration of dust and or late forming planets. Okay, that was starting to look really nice to me. It wasn't my idea. It was several other people's idea. But then we looked at this. We looked at, this is a plot from a paper with James Owen using the California Kepler survey sample. And the California Kepler survey, which you have hopefully heard of, shows this gap in planet radii at about 1.8 Earth radii. And it turns out that it's showing a signature almost certainly of some sort of planet evaporation. So that's really cool. I'm not going to talk about it right now. Right now, what I want to do is ignore all of the planets that Kepler found that are really close that could be affected by evaporation, and just look at the farthest most ones in the Kepler sample. So this is radius in Earth radii. This is period. And the difference here is that these are the low metallicity stars, and these are the high metallicity stars. So around the low metallicity stars, you can see, so this is that radius cut here, the dotted line, small versus large. And the idea is that the large ones didn't have their, still have gas atmospheres, and the small ones don't. You can see that the low metallicity stars have a lot more of the small planets comparatively, and the high metallicity stars, those large planets, get larger. So if you look at this, it looks like if you have a high metallicity star, you make bigger super Earths. Oops, sorry. Marta Bryan also has recently looked at super Earth systems and found that they often have gas giant companions around them. So both of those results really seem to put us up here. Like the high metallicity systems have more of the super Earth systems have gas giants, so it seems like we should be in this part of the plot. All right, so now I'm confused, right? Why don't we have more gas giants, if that's what's going on? Okay, so you can always say, well, there's not just one parameter, there's more than one parameter, and of course, that could well be right. But what I want to suggest is that actually maybe there are a lot of gas giants. Maybe we're just missing a large gas giant population out at large distances. And I'm going to go through several suggestions about this, but fundamentally, what I'm saying is that I would like to know what is the population of higher mass planets at large distances, and what actually are their masses. And can we understand this discrepancy between 1/3 of super Earths, 1/3 of stars having super Earths, and 1/6 having gas giants, if we can understand the statistics of the planet mass population at larger distances. All right, okay, so first of all, is it possible that we could have a lot of gas giants at large distances that we don't know? And I think the answer is yes. I'm going to show you a little bit of work by a great graduate student, Mickey Rosenthal, who will be graduating next year. He's a really fantastic theorist. And this is appealing to capture by gas drag of a growing core. So we call this gas-assisted growth. It's often called pebble accretion. And the basic idea is that if you have a little small planetesimal, it drifts into that hill radius or a modified hill radius around a core. It can come in, and gas drag can cause it to lose the relative kinetic energy with the core, and it will fly in and be accreted. All right. So we have to, when we're thinking about gas drag, a number of things about planet formation get modified. Instead of satellites being able to orbit within the hill radius, they made that a stability radius may be modified. If the relative gas drag between a core and a particle is so large that it outweighs gravity, then it gets pulled off. And when that happens, we call it instead the whoosh radius. So we have a new stability radius. But within whatever that radius is, you can get captured by dissipation, again, by gas drag. And this has also been worked on by Ormel and Clark, by Lambrecht and Johansen, and others. And this process can dramatically speed up the formation of cores. And I just want to make one physics point that I'm not going to go into in detail, but this is a plot from Mickey's paper showing that if you have the same core, the stability of, the ability of a particle to be captured depends on its size. So if you have a very small particle that's well coupled to the gas, it will just be pulled around the core. If it's a little bit bigger, a little less well coupled, it can be binary captured. And then if it's a little bit bigger again, then the gas doesn't matter and it will be pulled off. So what ends up happening is that there's actually only a small range of particle sizes, usually a couple of orders of magnitude in range, that can be captured for each core size. So without going into all of the gory details, and there are many, I have to say, in this theory, here's an example of this happening at different levels of turbulence. So here, blue means that the growth time is really small, so you can grow really well. This is particle size. This is core mass. And I'm just going to focus on this one here. This is turbulent alpha of 10 to the minus 2. You can see that there's a range of core masses here where you have range of particle sizes where it's blue, and you can have very fast growth. But you actually have to get up to a minimum mass before you can reach that fast growth regime. And that's because the turbulence makes the relative velocity so high that it's hard for capture to happen. And you can see that actually changes with the different turbulence levels. All right, so just in case you're wondering, there are plenty of pebbles to be accreted in protoplanetary disks. Here's a plot comparing to the minimum mass solar nebula. We see them, they're there. You can't say they're not there because we can actually see that they're there. We've actually tested, these are analytic calculations, but we've tested this with, Xian Zhu and Zhening Bai have tested this with numerical simulations. You can see the pebbles being accreted onto the middle. A lot of work has been done on this by other groups as well, including the work, as I said before, Ormel and Clark and Lambrecht and Johansen. Okay, so what can we do with this? If we have a minimum core mass for fast growth that depends on how much turbulence you have in your disk, then we can use that to estimate how far out in the disk gas giant growth is possible. And the key thing that I want you to see here is, in standard planet formation theory, as you grow and grow and grow, the growth gets slower and slower and slower until eventually it becomes too slow and it can't happen anymore. With pebble accretion, at least in this typical regime, it's the opposite. It doesn't work at low core masses, but once it works, it goes like gangbusters. So basically, you need to have a minimum core mass for pebble accretion to kick in. And as long as you're able to grow by standard processes up to that minimum core mass, in principle, you should be able to grow your core. Where those timescales cross is where the growth of gas giants doesn't become possible anymore. All right, so we can do that with different levels of accretion. Here's that planetesimal growth. And you can see, of course, that at low turbulence, you can grow gas giants farther out in the disk because turbulence isn't preventing this growth process. And we can do that explicitly. Here's the turbulent level of alpha, the distance you can grow your gas giant, and we can make a plot. You can see that as the turbulence level goes up, the distance you can make gas giants at goes down. So if this is the physics that determines whether you form a giant planet or not, then where you grow your planet depends on your turbulence level. Okay, so I want to remind you that direct imaging surveys have, of course, looked for giant planets around a large number of stars and have not found that many. But this is their typical mass limit. It's about 2 Jupiter masses. So if you were looking for a mass distribution that matched that in the inner systems of observed radial velocity systems, then absolutely you should have seen those things, because those masses go way up all the way to 20 Jupiter masses. But if your gas giants were more like Jupiter or Saturn and below 2 Jupiter masses, we would have no way of seeing them. So that's the limit. And here, just as an example, is a scenario in which you would make giants that are less than 2 Jupiter masses. So let me take a step back and say, once you've grown a planet by core accretion, it has to reach a minimum core mass to go runaway. But that doesn't tell you what mass it ultimately gets to. Like, that physics is something else. We often assume that it's gap starvation. You open such a wide gap in the disk that you stop growing. This here is a very simplistic gap starvation model. I think Judith's going to be talking about another way that this stops later today. So this is this is not an involved model, but it has a sign that I think is correct. So here, what this shows is the distance where, for different turbulence values, the distance where turbulence stops core growth, and the mass that you would form that planet with using a simple gap starvation model. So check this out. Low turbulence, far out in the disk, low mass. Okay, high turbulence, you can't form them far out, but you have a high mass. So maybe out at large distances, there are a bunch of gas giants. They're just lower mass than we've seen so far. I'll be interested to see what Judith says about that. All right, okay. Okay, so hypothesis, maybe gas giants are more common than we think. They're just less massive than direct imaging limits. I think that's totally conceivable, and I would like to know from microlensing if that's the case. Okay, how much less massive? I hear from you guys that super Neptune sub-Saturns are really common. That's super weird. Why would they stop at that mass? I don't get it. Okay, if it's true, maybe they're much less massive. Those are definitely super critical sorts of things. They should have a bunch of gas. From this perspective, I accept those. And again, robust models of the physical processes that cut off that gas are needed, accretion are needed. All right, okay, very brief aside. What about gravitational instability? A while ago, with Caitlin Crater and Andrew Uden, I worked on gravitational instability as a possible explanation for HR 8799. I'm not going to go into this right now, but for those of you who've been paying attention, we said, well, if there are a bunch of planets here that are, brown dwarfs, then maybe that could be the tail of that distribution. Well, it looks like there kind of are, so maybe it's not dead. I mean, it's clearly not a common process, but HR 8799, I don't know, maybe it still could be a gravitational instability body. Maybe it's not typical of those objects. I would like to know if it's part of the overall giant mass distribution. Yes?
What's gray and what's red here?
This is from Brendan Bowler in review. These are the radial velocity planets, and these are the direct imaging planets. I think this is not intended to be a statistically uniform plot. I have strong confidence in that statement. It's just there are some there. So, maybe it's a 1% effect. So that's another thing I'd like to know. I'd still like to know, are these the tail of the giant planet distribution or not? You know, they could still be the tail of the brown dwarf distribution, and we could be looking for a different tail, a different giant planet population. Okay, all right. So in summary of my talk, and then I'll go on to Renata's because it's very related. Larger super-Earth cores are around high metallicity stars, and Marta Bryan has found that super-Earth cores have gas giant companions. So are giant planets more common than we think? And maybe that means super Neptunes. I'm not sure. Also, disk turbulence may set the outer distance and mass scale of giant planet formation. So I want to know, does the separation distribution of giants depend on their mass? And for both of these questions, I'm interested in knowing that for, for anything that's too big to be just a rock. All right. Okay. And that leads to Renata's project, which is to ask ourselves, then why would the planets in the inner system that we see with radial velocities be so different than the ones in the outer system? And what I'd like to know, or what we'd like to know, is whether there could have been a phase of planet-planet impacts for gas giants in the inner planetary system. Now, you can ask all the questions that I asked before, whether you like this idea or not, but I think that it's quite interesting. Okay, so recall, there are a bunch of high eccentricity gas giants. So when we look at the planets that the radial velocity method has found, they're all really dynamically excited. So something has gone on here. All right. So I also claimed that maybe they were smeared out compared to the low metallicity systems. Now let's look at this a different way. This is from Rebecca Dawson back in 2013. Here's distance from the star, 1 minus eccentricity squared. So down here is high eccentricity. If you look at these radial velocity planets, the high eccentricity planets between 0.1 and 1 AU are all around metal-rich stars. Blue means metallicity greater than 0. So our interpretation at the time was that this suggested planet-planet interactions, because why should metallicity matter for this? Well, if you have more planets, maybe more metallicity, more planets, you have more dynamics. All right, let's look at this one more way. Here's mass of your planet. Again, this is radial velocity planets, eccentricity. Check it out. Eccentricities are higher for higher mass planets. That's kind of weird, actually, right? Wouldn't you expect the lower mass planets to have the higher eccentricities because they can be scattered more easily? Well, they don't. Also, the highest masses and eccentricities are in the high metallicity systems. So maybe that gives us a clue, right? So maybe they have the high eccentricities because they were the systems that had a lot of planets, and so they get scattered the most. All right, so maybe more massive systems have more dynamical interactions. All right, so let's go back. Remember that we said that in the solar system, there was supposed to be this large giant impact phase at the end of growth. Well, what causes giant impact phases? Well, it's the difference between scattering, collisions, and escape from your system. So let's give me a moment on this slide. If you look at this first, if the relative velocity between something colliding with you is less than your escape velocity, then you have gravitational focusing, right? So you actually have a big cross-section for strong scatterings. If it's the other way around, if your relative velocity is greater than the surface escape velocity, you're going to collide rather than scatter. Okay, so in the inner system, you keep getting excited by these scatterings until velocities are larger than the escape velocity and you start having a lot of collisions. But in outer systems, you keep getting excited and you keep getting excited and then, oops, suddenly you escape from the system. So you get ejected rather than colliding. So none of that said, so yeah, Earth and Jupiter have different escape velocities, but they're not that different. This is all about whether you're close to your star or whether you're far away. It's not about whether you're a rock or a giant planet. Okay, so could we have a giant impact stage for giant planets? Well, let's just decide that we do and see where we can go. And so we're going to have to make a non-standard assumption. And I fully accept that it's non-standard, but it's at least related to the last thing that I was saying in the previous talk. That is that you have a bunch of giant planets that are a lot lower mass than we think, instead of having a few giant planets when you start. Enough, 5, 7, something like that, so that you have a lot of interactions. You might feel unhappy about that. I feel a little bit unhappy about that. So I'm with you. But if you're willing to take that leap and say that you don't make them big, you only make them small, then we can actually get to some interesting places. Okay, so first of all, we said that you have scattering or collisions, and here's the system escape. So what this means, putting it all together, is that the maximum eccentricity that you can get to is your relative velocity divided by your orbital velocity. Because once you get up to that eccentricity, collisions will set in. And if this number becomes greater than 1, you get ejected instead of colliding. All right, so we can do some numerical simulations to test out this idea. I didn't put his name with apologies. Cristobal Petrovich has also been involved in this work. And you can see that both in our simulations and in the radial velocity observations, you could interpret the edge of the data as an eccentricity envelope coming from scattering. Okay. But now, let's take our assumption that we have a lot of small gas giants and allow them to collide as they grow. They grow through collisions. They end up with giants with masses up to about half the total initial mass in planets, a lot bigger than they started. And you can match what I'm about to show you on the data at least amusingly well. I think it's exciting. So we pick a range of disk masses that's designed specifically to match the planet mass in the observations. So that's how we pick the disk masses that we're starting with. And it turns out that once you pick your disk mass, as long as you have, by disk mass, I mean mass in giants that I'm starting with. And as long as you start with more than 7-ish, 5-ish, it doesn't really matter how many you start with. You could start with 50 if you wanted, and they'd be really little. And you get something that was pretty similar. Okay, so here we are. So we have a mass, eccentricity, and this is metallicity. Now, with apologies, high metallicity is now red, and low metallicity is blue. We didn't have a chance to swap because of the family emergency. Apologies. Okay, high metallicity is red. Here's the RV observations. This is what we showed before, mass versus eccentricity. The high mass ones have the highest eccentricity, and they also have high metallicities. In our simulations, you get the same thing. The high mass planets have the highest eccentricities. They also have the high metallicities, which we've connected to our initial disk mass. I just want to point out that these are the same contour levels, and all we did was pick disk masses to match the current mass distribution of planets. So we didn't tune a whole lot here. Okay, I'll show you a couple other things. Here's the semi-major axis versus eccentricity. And now we're cutting this on planet mass. At large semi-major axes in the observations, you have higher planet masses. The same is true in these simulations. And if you look at semi-major axis versus eccentricity, these high eccentricity planets that are going up to that eccentricity envelope in both cases. You should just look at the dark curve here, all around high metallicity stars. So we were able to get eccentricities that were, maybe they're a little bit lower. They're almost up there. We didn't, as I said, we didn't fuss around with tuning this a whole lot. We just picked some disks that match the planet mass distribution. And you can get some really nice correlations with the data. All right, okay. So the observed giant planet eccentricities, maybe they result from a giant impact phase. If so, very massive giants will be easier. Growth of massive giants is easier in the inner system, where ejection is difficult. Out at large distances, you'd expect to still have the smaller things. That applies to ejected planets too, right? So if this is right, the prediction is that maximum masses of observed giant planets should decline with stellocentric separation. And I'll just note that this is the opposite sign from what you would get if you were making individual giants by opening gaps in the disk, because as you go out and, to large distances in the disk, it becomes harder to isolate yourself from the gas. All right, okay, so I will conclude with, I'm interested to see what the mass and distance separation of planets is from W first. I hope that you are able to get those data. Thank you.
Matthew.
Do you say that in all of it, or in general, or even only in specific cases, is planet mass a more natural variable, or is mass ratio to the star?
I would say that that depends on whether the disk mass scales with the stellar mass. That's a good question, and I should think through the answer to that. For growth by pebble accretion, you end up growing to your thermal mass and then being isolated from the pebbles. So that's going to scale more with luminosity of your star. So it's not quite going to be mass ratio. It just depends on what actually sets that final gas giant mass. So if we're talking about giants, I guess maybe that's the answer. It depends on what sets the mass. So we'll see what Judith has to say. And there's also more work to be done on the gap clearing.
So you didn't say much about, excuse me, host mass here. Work by Ben Monte and stuff I did with Kristen Clinton showed that for planets, if you define them giant planets as greater than 1 Jupiter mass, then there are fewer around M dwarfs, but only by a factor of 2, and there's large error bars. But if you define giant planets as anything over sort of 30 Earth masses, where you might expect runaway to have happened, then the difference becomes smaller between planets around M dwarfs and solar type stars scaled to some version of the snow line or something.
Yeah.
Does that jive with this?
Yeah, I mean,
Yeah.
It doesn't not jive with it,
Okay,
but
all right.
I mean, I'm not sure that it's a just specific.
Okay.
Yeah.
But is it evidence for this overall picture you have? It's not obvious to me.
Because most of the super Earth statistics are not around M stars, I'm not sure it's directly evidence for what I was exactly saying, but I absolutely think it fits into this picture. Yeah.
So, there are 2 existing probes for your question. One is so if there's a lot of planets that are very far away, they're going to show up as free-floating planets. And Primary, I think, has, will know his statistics better than I do, but I think it's something like less than 0.2 planets per star, something like that. But he'll comment. And the second is that if you look at, so these would just be things that appear as short bumps, and they could be mixed up with stars. So there's this distribution that you have to subtract out from. But then in addition, there's for every microlensing event, there's some chance of running into a planet in the outlying area, which is more or less the square root of the planet-star mass ratio. So that's like the 1/30 times the number of Einstein radii that you are away, which I guess for 50 AU would be your typical number, then that'd be like 25. So anyway, 1 in 1,000. So there have been 20,000 microlensing events discovered, and Radek here somewhere, has looked for, well, not in all 20,000 of them because there's not good enough data, but anyway, there's been pretty exhaustive search for these insofar as they can be found in the data. It'd be better if these two people comment on this than me because I know the idea but don't know the numbers.
I'd love to dig into those data. Thank you. Yeah, just one quick comment, which is to address the 1/3 versus 1/6. We just need to go out beyond the 5-ish AU that the radial velocities get to. We don't necessarily need to go all the way out to 50, but
No, but
Yeah.
isn't it? I thought that these 1/6 would be somewhere in this, tens of AU range, and we'd have to
Well,
collect all of them.
the 1/6 is an extrapolation from the radial velocity data, which only actually is measured out to 5 AU. So
But anyway, what you're finding out about is just bolometric, everything that's there.
Yeah.
That's the measurement.
yeah, well, if you have, I'd love to see those data in more
Great.
detail. Great, thanks.
Jennifer.
So, okay. So your prediction is framed in terms of the maximum mass of observed giant planets, but would it also predict something about the distribution in mass? at the
Yeah,
far
there's
side?
going to be an initial mass, input there as well, right? So we need to know how far out the giants go. But yeah. I mean, it may well also be the case that the initial mass that you make the giants before they dynamically interact changes as you go out in the disk. So it could easily be a little more complicated, which is why I stuck to the qualitative distribution. But yes, you could make predictions about the distribution. Yeah.
Wei.
I have two comments. First, you showed a plot from the Owen and Mary Clay paper showing from 20 to 100 days there are fewer super Earths or mini Neptunes in the metal-rich environment. However, I think that's just that's because of the multiplanetary systems. Because as you also said, there are super Earths more often have cold giant companions, and these cold giant companions can reduce the number of super Earths. Therefore, if you go to high metallicity, there are more systems with super Earths, but the total number of super Earths is smaller. So that's the first comment. The second comment is
so just to respond to that, so we were not in that paper. We didn't have the normalization. So that paper isn't talking about the absolute numbers. It's talking about the relative numbers of super Earths compared to lower mass things.
Yes, but you're talking about the number of super Earths instead of the number
compared
of
to it's the ratio
systems.
of small to large ones, small planets that are below the radius gap to above the radius gap.
Yeah, but that's the number of super Earths. Metallicity is a system parameter, therefore you should use the number of super Earth systems instead of number of super Earths.
So again, when we wrote that paper, and since people have done an analysis that includes, the Fulton group has done an analysis that includes the number of planets, stars they searched. We didn't have the number of stars they searched. So all we were looking at is the relative number. They're all super Earths. Both the small and the large ones are super Earths. It's the relative number of ones below the radius gap, so they don't have atmospheres, to above. So at close in, that's likely set by evaporation. But the idea is that if we're looking far enough out, then that should be set by formation. So if you weren't able to photoevaporate, so you never got that envelope. Now, I fully agree, if I understand your question, which that at those distances, the statistics aren't as good as at closer in distances. So we could use better statistics there. There may be other theoretical explanations, but I'm just showing the data.
Okay, fine. We can talk about that more. The second comment is you said there are this Brian et al. Results show there are more super systems have cogiant companions. In fact, our work, Zhu and Wu was the first one to point this out. And furthermore, we also showed if you invert this conditional probability, almost all the co-Jupiters or co-giants should have inner super Earths or small planets. That's just a comment.
Thanks. Could you send me that reference, please?
Yeah, sure.
Actually, is that the reference with Yenchen?
Yes.
Okay, then I have read it, and I apologize for not mentioning it. You're right.
Any more questions? Okay, let's thank Ruth again. Okay, our next talk is by Judith Sulagi from University of Zurich about formation of intermediate mass gas giant planets through circumplanetary disk accretion.
Thank you very much, and thank you very much for the invitation. Indeed, I'm working at University of Zurich. I'm a junior group leader there. So one of our major planet formation scenario is the core accretion scenario by Pollack et al. And collaborators. It has three main stages, as I color-coded over here for you. In the first case, in the first stage, we are coagulating the solid core, and then the planet grows to roughly 10 Earth masses. Then the planet is massive enough to starting to hold gas around it. This is when we enter the slow gas envelope accretion phase. This is the second phase. And by the time the envelope becomes equal in mass with the core, then the self-gravity of the gas will starting to dominate. The gas envelope will collapse onto the core, and we'll drag in more and more gas. And this is when the planet enters the so-called runaway gas accretion regime, when it thought to form exponentially. This model of Pollack was originally one-dimensional, and it predicted that in this third phase, basically within 10,000 years, we would form a Jupiter mass planet. So that would mean an accretion rate of 10 to the minus 4 Jupiter mass per year. And please remember this because it will be important later on. The problem with this model, as we have heard already, that it would not result in any intermediate mass planets that we see by observation. Instead, it would have predicted a bimodal planetary mass distribution. The cores will remain in the second phase and remain roughly this between 10 and 20 Earth masses, or they enter the runaway phase and very quickly complete it within 10,000 years, and we would get Jupiter mass planets or several Jupiter mass planets and nothing in between. But as you know here very well, that the observational evidence is showing us otherwise. Between the 10 Earth masses and the Saturn mass cases, we have quite many planets over there, and now the new microlensing results, the Suzuki et al. Paper, shows that intermediate mass giants are more numerous than giant planets. So definitely there is something with the runaway accretion which needs to be altered. So the original model was one-dimensional, therefore it could only account for a spherical accretion, and that meant an exponential growth. But we who are doing simulations of planet formation, we see that actually in this third phase, a circumplanetary disk forms around the planet. This is one of my simulations of that, which we know since 1999, actually, and all of us are getting the same. We know that this circumplanetary disk formation is not just an artifact of the simulations, because the satellites of giant planets are thought to form in those disks. So the presence of satellites around giant planets are suggesting that indeed this circumplanetary disk forms, and now you understand that we are breaking away from the 1D spherical accretion very much so. So this is one of my simulations of a forming 3 Jupiter mass planet over here. As we zoom close to the planet vicinity, you see the circumplanetary disk, and I also plotted the gas streamlines, so how the gas is flowing onto the planet and in the planet vicinity. As you see from the outer disk, from the high colatitude regions, the gas will come in and spiral down to the planet. And actually, inside the circumplanetary disk, it will spiral outwards, pushing back gas into the circumstellar disk. So the circumplanetary disk is a deaccretional disk, if you wish. This is the, I named it meridional circulation in my 2014 work, and since then, Berkeley group have also confirmed these results. So this is the schematics of the previous video. So what you see here, that the gas is continuously trying to close the gap what the planet opened, and as the gas will fall into the gap, it will feel the planet gravity, and it will free fall onto the circumplanetary disk and onto the planet itself. And that part of the gas, which could not be accreted right away, will be pushed back in the midplane regions, back to the circumstellar disk, and this gas then rising up again to maintain this meridional circulation. As you see, this is really a 3D mechanism. So in a 1D model, we could not account for such a complex accretion. So in the runaway phase. So this is one of the reasons why we are different in comparison to the Pollack model, and this is one of the reasons what slows down the accretion. Now we have a disk-limited accretion instead of a spherical envelope accretion. And the second point I want to make, which is also super important, it turned out the thermal effects will have a huge impact on the accretion rate. That is because the accretion, of course, heats up the planet and its vicinity. And as the gas is heated up, it wants to expand. And this expansion is driving a gas pressure, which will act against the accretion and will slow down the accretion. That's actually about this Ruth already talked about in a little bit different way. So then people used to ask me that why is that hydrodynamic simulations before have gotten the same runaway accretion rate, so that 10 to the minus 4 Jupiter mass per year in, say, 10 years ago or 15 years ago. Well, as every field, our field is also evolving, and we are capable of putting in more and more physical complexity in our simulations. But also, the computers are getting more and more fast, and therefore we can account for many more effects and having higher resolution than it was possible before. So, 10 years ago, or even 5 years ago, actually, many of us were still running 2D simulations in the midplane, which could not account for the 3D accretion flow what we see. Also, at that point, we did not have fast enough computers to put in all the thermal effects, stellar irradiation, accretional heating, viscous heating, that what we can put in today. Also, at that point, in the community, people have used the same method like the black hole community. They set up a sink at the location of the planet, assuming that the accretion process is 100% efficient. And they would carve out the mass or density in the planet region every single time step. And of course, this way, the gas in the neighboring cells will flow onto the vacuum very efficiently. I call it the vacuum cleaner effect because I think it's a good prescription that indeed it enhances the accretion rate. However, I keep saying that the planet is not a black hole. It is a hot ball of gas and will not have this accretional efficiency. And I think creating a vacuum in the simulations is not the right way to measure the accretion. Also, say 10 years ago, or even 5 years ago, we did not have the resolution to reach the planet's surface. And when we talk about planetary accretion, we really need to resolve the planet in order to measure the accretion rate on the surface. As Ruth already mentioned about the heliosphere, before people have thought that every gas molecule which will enter the heliosphere will end up on the planet. So they thought that the heliosphere accretion rate will be equal to the planet accretion rate. As you saw in the video or even in the meridional circulation plot, there is quite some outflow also from the heliosphere. So it's not true that everything that enters in the heliosphere will end up on the planet. And also, I am really much advocating for the fact that when you run simulations, you should know your errors. And people have, Willy Klein group started to get into measuring the numerical viscosity. This is the errors that we make when we solve the partial differential equations. And these errors are propagating and acting like an extra source of viscosity in our simulations. And viscosity is driving accretion rate. in my calculation, in my case, the numerical viscosity enhances the accretion rate by a factor of 40. So that is 1.5 orders of magnitude. So therefore, I think we should all really look into the errors and numerical artifacts our simulations are getting when we are talking about accretion rates. So the accretion rates I was getting for a Jupiter mass planet, or the formation of a Jupiter mass planet, on average were already like on the order of 10 to the minus 6 Jupiter mass per year, which is 2 orders of magnitude slower than the original runaway prediction, just because I accounted for the numerical viscosity, I did not have massing, and so on. I was the previous points I was talking about. And when I coded in all the thermal effects, the stellar irradiation, the accretional heating, the radiative dissipation, viscous heating, then I got even lower accretion rate, 10 to the minus 7, 10 to the minus 9 on the order. And now, since other people with other codes have also getting very similar accretion rates, when they also including those thermal effects, I included. So it seems like now we are having the opposite problem, that it's difficult to form giant planets, because if you look at here, this would mean that to build up a Jupiter mass planet, we need almost 10 to the 9 years. And of course, the circumstellar disk doesn't live that long. So what controls really the accretion rate? Well, what I'm getting in the simulation is that the hotter is the gas, the lower is the accretion rate. And why is that? The hotter means that the opacity is higher locally. And this idea is not mine. It has been around in the community by many people, analytical works, but also simulations, the piezo work, which Ruth was part of. Really, high opacity means low accretion rate. And because of that, we need to understand better the formation, the forming planet opacities and temperatures, because that would determine how much gas they can accommodate or accrete. Also, as everybody knows, closer to the star, the temperatures are higher. That would mean, in general, lower accretion rate. So all in all, we can form higher mass giant planets in colder places or low opacity places. In other words, for example, in the outer disk. And I'm really much advocating for this idea, which was basically, I think, Pizzo, who have put that forward first. And I would like to just point out that this whole idea is nothing new. In other parts of astrophysics, people have known this in AGNs, massive star formation, gravitational instability, planet formation, that if there is a cloud of gas and it's heated up, it wants to expand and it will go against collapse and accretion. So this idea is just the same physics. And in the core accretion community, we are just catching up with the other parts of astrophysics. So in conclusion, I think we can say that the original runaway accretion seems to have some challenges, both observationally and simulation-wise. We see that disk is forming in this phase, and we see that thermal effects really dominate and matter very much for the accretion rate. However, I would like to point out, of course, our simulations are still not the best. I personally would like to put in magnetic fields and self-gravity as well in order to address better the question, but for that I need to wait faster computers, because now my simulations are running like 3 months on a world highest, fastest supercomputer, so it's still not there that I could put in more physics. But all in all, we can see that the observed smooth mass distribution of planets might be caused by the temperature and opacity gradient of the disk and the local thermal and opacity effects near the planet. And for this reason, we need to understand much better the opacity of the disk and the forming planet, because that will set the accretion rate. So thank you very much.
Andy?
So still the RV has a dip, even if it doesn't have a gap. And maybe the microlensing is not totally inconsistent with that, I'm not sure. But anyway, does that naturally falling out of this picture, you know, because the, you know, the supposedly there was, you know, great difficulty building up to Neptune masses, and then you get this runaway. But anyway, maybe there's still the same thing of difficulty and then some kind of slower process.
Yeah, so I believe that that we need to understand this part, the opacity, or what Ruth said is metallicity, but it's kind of the same idea. The higher opacity or more dust we have, the slower is going to be the accretion rate. But how it is changes within the disk is not understood yet, and what is the opacity of forming planets is not understood. So I think if you understand that, then we can have a more prediction regarding the mass distribution. I don't know whether it would still have some peak and depth on the intermediate mass planets or not. But these parts were not put in the population synthesis work so far. So I think these parts should be included now, and I'm working on trying to provide predictions for population synthesis work so that they can put that in and see whether there are going to be any deep depth or anything there, or what kind of mass distribution we are going to get out.
What's the lower mass limit of what this applies to?
Oh, of the formation of the circumplanetary disk, or what is the lower mass?
Oh, your work, have you only simulated?
Yeah.
down to
So
some
I have
mass?
just a new paper out that was about Uranus and Neptune that shows that even Uranus and Neptune could have formed a circumplanetary disk very late, though. Very late during their formation, just before the circumstellar disk dissipated, but even those massive planets can eventually form a disk. And this is why, by the way, the Uranus satellite system could have formed in that disk.
You said that lower temperatures allow you to get to higher masses, right?
Exactly.
So, so when we think about Jupiter and Saturn, Saturn's colder, but it's lower mass. So how do you do that?
Yeah, so that's why I said that not only the disk, but the local effects also we need to understand. It could be that, I mean, they migrated, right? So we don't know what was the opacity or the temperature at the point where they actually born. So I think we wouldn't be able to say, but all these kind of fluctuations can lead to the different final masses that we see.
So it seems the thermal state is very important. Does it mean it has a very sensitive dependence on the host star mass, the planet formation efficiency?
So in my simulation, the host star mass comes in like in the stellar irradiation part, if you wish. But actually, the stellar irradiation doesn't really have too much effect at the planet location because, as you saw before, the planet is really shielded by the inner circumstellar disk, so this part. So here is the star, and this part is very much absorbing the stellar photons, and so not many gets into this region. So actually what is controlling really much the temperature around here is what is the planet temperature, if you wish. And this is what we don't know because there are no evolutionary works during the formation phase for planets. We just know it's a few thousand K, but whether it's 1,000 K or 10,000 K, we don't know. And that gives a different results regarding the accretion rates.
I have a related question. I think, because my understanding is in the outer parts of planetary disks, it's not stellar irradiation, it's accretional heating or viscosity that actually sets the mid-plane temperature. But you also have some regions where it's cold enough that you have a dead zone.
Exactly.
How would that affect? You're assuming some sort of viscosity?
Yes.
Right? If you had, essentially no viscosity, what would you predict?
Yeah, so that I did that already, and that already was that was the 14 work actually. So yeah, it already gives you much lower accretion rate, but that's because I think mainly the numerical viscosity was accounted for. So all in all, the main heating mechanism near the planet is the accretion. Okay, so the viscosity has to be super large in order the viscous heating would dominate. So it still seems like that the planet's accretion, the adiabatic compression, as the gas wanting to fall onto the planet potential is the main source of heating, at least in most of my simulations. But I still use usually very small viscosity, because I think now we kind of agree that this alpha viscosity model is maybe not the best, and we're supposed to have very low turbulence based on the ALMA data. So I just use very small viscosities in general.
Just a comment that if you want to make small planets by any of these mechanisms, small giants, you want low viscosity. So thankfully, Alma's on your side for that.
Yeah.
Let's thank Judith again. Okay, our next speaker is Wei Zhu, talking about a pair of planets likely in mean motion resonance from gravitational microlensing.
Right, thanks. So last year in New Zealand, I gave a talk about how to get constraints on the 3D orbits of planets from the stability analysis using this particular two-planet system as an example. And then later that summer, I had a summer student, Sabrina Madison, from University of British Columbia to work with me on to try to work out this idea. And in the end, we proved that what I said last year was totally wrong. So I'm going to explain you what is right. And the result is given in this paper, which shown on arXiv very recently. So why is it hard to get optical information about microlensing planets from microlensing, right? So this is a plot from Scott's review paper, and you can see microlensing is probing the planets close to and slightly beyond the snow line, and the optical periods of these planets are typically a few years. But the microlensing timescale, which is the Einstein timescale, is typically only a month, and the planetary perturbation is only typically a few days. So therefore, microlensing typically only tell you just the projected configuration of the planetary system. Now, in very rare cases, you can get constraints on the orbits of either the planet or the binary stars in this case. So I'm showing the plots for this binary system, which analyzed in Scoria and all, and then followed up in radial velocity by Jennifer and several others. And you can see for this very bright and very close binary, you got very good constraints from the microlensing, well, reasonably good constraints on the orbits from microlensing light curve modeling. And then with together with the radial velocity follow-up, you got almost very precise constraints on, for example, eccentricity and optical period of these planets. But you don't often have this for most of the microlensing systems. And here I'm just listing some of the good examples where you did get this kind of constraints. And therefore, how do you do? Because, well, if you want to constrain the, for example, use microlensing planets to constrain the planet formation or planet evolution theory, then you might be interested in knowing the real semi-major axis instead of the projected separation and the eccentricity of the planet or the binaries. So a lesson we learned from the direct imaging or radial velocity and transit as well is that you can, for this in particular, the multiplanetary systems, you can use the stability to constrain their orbits. So this is a work done by Ruth and Dan Fabric here a few years ago for this direct imaging system, HR 8799. Back then, there were only 3 planets found, but later on there was another one. What they found is that in order to keep this whole system stable, more likely the 3 planets, B, C, and D, are in a doubly 2-to-1 mean motion resonance. So the plot shown on the right is if you're in a rotating frame with the planet C, then the planet D has to be further away from the planet C when it's getting closer to planet C, and getting to a longer separation when it's largely separated azimuthally. So there's 2-to-1 mean motion resonance basically means when the inner planet orbits twice, the outer planet orbits once, and keeps the whole system from dynamically unstable. And there are lots of similarities between direct imaging systems and microlensing, because in microlensing, we also, well, in direct imaging, they also probe the projected positions of the planets. And if you wait long enough, you can see the planet moves. So you got one-dimensional, well, basically the linear velocities of the planets. So we got that in microlensing as well, sometimes. So, but what we have more in microlensing is that we have we also got the planet to star mass ratio, which is more relevant for dynamical analysis. So this is the system, two-planet system I'm focusing on from the High-end paper, and there were AO observations from GP's work to constrain the mass of the system. But that does not matter too much, because we have very well constrained mass ratios of both planets. So the light curve shown on the right, on the left, and then there are 4 allowed solutions because of the close-wide degeneracy. So the 2 planets could be either both inside the Einstein ring or both outside the Einstein ring. And the mass ratio, one is 10 to the minus 4, the other is close to 10 to the minus 3. And you can see for all these allowed solutions, the planets, both planets, are very close to the Einstein ring. One is only 5% off from the Einstein ring, the other is 25% off from the Einstein ring. So the point is the 2 planets are very close to each other in this projected plane. Of course, you can have these inclinations. You can incline the whole system so that the 2 planets could be further away, even though they appear close to each other in the projected plane. But if you just assume the inclination is isotropically distributed, then the fact that you see these 2 planets are very close to each other in this projected plane actually means the 2 planets statistically should be very close to each other in their real side major access ratio. So basically, if so, this is the model I'm considering here. So the 2 planets are shown in here relative to the star, and if you want to incline the system, then the 2 planets could be further separated. But if you, in fact, if you go to a very high inclination, like edge-on configuration, of course, the 2 planets could be much further separated. But in that case, you would expect to see the 2 planets to be aligned with the star. But that's not what you see here. Therefore, this azimuthal separation between the 2 planets disfavors this high inclination configuration. And on the other hand, if you go to this very small inclination close to face-on, then, well, as a priori, the inclination follows as sine I. So essentially, there's zero chance to have a really face-on configuration. So taking both into account, you got this inclination distribution, and you got side major access ratio, which you can convert into this period ratio, and you can see it strongly picks at what you would expect from just inverting the projected separation ratio into period ratio. And you can also try to incline the 2 planets relative to each other, but that does not help too much. So the point from this analysis is that the 2 planets, the fact that the 2 planets are close to each other in this projected plane means statistically the 2 planets are close to each other in this 3D configuration. And most likely the 2 planets should have a period ratio closer than 2. Now, why is that important? Well, so once you know these 2 planets are more likely have this period ratio that you got from the projected separation, then you can just randomly give velocities to either planets or both planets and run some n-body simulations and see which kind of configurations are stable. So this is the result we got on this eccentricity versus opto period ratio plots, or the points each point is a stable configuration for a randomized eccentricity vector or velocity, essentially. Now you can say, so this is where you would have if you have 0 eccentricity or close here, then you increase eccentricity, then lots of the systems become unstable, and in the end, you only have generally two types of configurations. Either the planets are eccentric and near these mean motion resonances, or in this mean motion resonance, all the planets must be nearly circular orbits and out of the mean motion resonance. Now, why point 1 is interesting, because point 1 is generally considered the largest eccentricity you can get from a protoplanetary disk. Now, if you look at similar planet pairs from radial velocity studies on the same scale, eccentricity versus orbital period, known radial velocity pairs, and all the blue dots are the planet pairs that are confirmed by dynamic analysis that should be in mean motion resonance in order to keep the system stable, except maybe this one, but this system has a giant star, so maybe the system has evolved after the main sequence. So therefore, you can say there's no planets in this region, and very likely this is the preferred. So the mean motion resonance is the preferred state. So theoretically, this agrees with our understanding of planet formation as well. So this is the plot showing how you can form a pair of planets in mean motion resonance. So you start from two planets out of resonance, then they go, they start from well separated, but then they converge towards each other, then they got caught in mean motion resonance, in this case 2 to 1 as well. And when they get caught, then all other dissipation forces goes into increase the eccentricity, and you end up with two eccentric planets, but locked in mean motion resonance. So that explains why you cannot have planets here, because if you want to form planets very close to each other, but out of resonance and 0 eccentricity, you have to go cross the mean motion resonance first. But if you are able to cross the mean motion resonance, you will go very fast to the next one. It's very hard to stop the planet out of mean motion resonance and remaining almost 0 eccentricity. Therefore, we think the two planets in this case are very close, very likely in this mean motion resonance. And the key ingredients is, first, the two planets are very close to each other, and they have some azimuthal offset. Now, there are more systems. We should have more similar system from Microlensing, because we probe planets very close to the Einstein ring, and from observations and simulations, we don't seem to have a preference on this azimuthal angle, or this angle phi here. So this is a final slide, which shows the ongoing work that I'm trying to connect different planet populations from different studies, different techniques. And there's a missing link here from radial velocity and microlensing by probing the cold Neptunes. And there are lots of unknown interesting questions to answer if we consider or study the microlensing multiplicity. And thank you.
Ruth?
Or will there be statistics for systems like this, ultimately?
If we have more systems like this, then we will have some statistical results.
Particularly for the cold Jupiters versus cold Neptunes? That would be
Oh,
really...
you mean this one?
Yeah, you asked, do cold Jupiters frequently have cold Neptunes? Is that a question that will be answerable with?
Well, we sort of answered a little bit in the paper, in this paper, but it's not fully taking into account the detection efficiencies. But our very rough estimate is almost all the cold Jupiters should have cold Neptunes.
What about the inverse? But I'll let other people ask. I'll ask you later.
So, in answer to Ruth's question, I mean, in previous simulations I did for a space-based microlensing survey, there's a very good chance of detecting the cold Jupiters when you detect the cold Neptunes. The other way around is a little bit harder, just because detection efficiency for the massive planets is higher. The question I had for Wei was, so you didn't say that much about the mutual inclinations, but if the mutual inclination of the two planets is 180 degrees, then I would think your constraints would be much weaker.
Sure, that you have two anti-rotating planets that could be more stable, but believe whether or not that.
And so then my other question is whether a 90-degree inclination would be stable. I mean, it is for polar ring galaxies, but
I have the referee of our paper. Anyway, but yeah, no, statistically, well, theoretically, yes, but statistically, it's hard because one system, let's say one system is phased on, the other system is agile, so that's 90 degree, but that system should be very far away. And what's the chance to have such a planet and in such a configuration?
Did you discuss that point in the paper?
Which?
Polar orbit. You just measure.
Oh, no, not yet. That's a question we will address.
Then why you ask, the question, did you read, your paper? So.
Well, that's a comment in the referee report.
Okay, let's thank Wei. Oh, oops, you had a question. Okay.
Isn't there a bias against detecting planets in the 180 or 0 from the fact that they both produce shear and going the same way and going to be absorbed into a single planet? Actually, isn't this shown in your 2014 papers?
No, we didn't. We said there's no reference, no bias towards that statistically. Well, maybe the sample was too small, but.
Okay, let's thank Wei.
Right, thanks.
Okay, our next speaker is Yossi from IPAC talking about the galactic distribution of planets via Spitzer microlensing campaigns.
Okay, thank you. So I'll give an update about our Spitzer microlensing campaigns. And the main goal of these campaigns is to constrain the galactic distribution of planets. And the key thing is to, when you look at the planet's mass versus distance from the solar system of all planets that we know, you can see that the red points, which are the microlensing, is basically the only technique that can probe this regime. This is the only technique that can answer the question, what is the planet formation efficiency in different galactic environments, specifically between the bulge and the disk, where we expect to have different, or might have different frequencies. However, when you look carefully on these microlensing planets, you can see that only for the nearby planets, we actually have direct distance measurements. And the reason for that is that we usually need microlensing parallax to detect these, and microlensing parallax signal is larger for nearby planets, and therefore we can detect these also with orbital parallax. That is the standard way. You can also do this with lens flux measurements. Lens flux measurements are more difficult. First thing is that it's a lot of resources, and you need to wait a lot of time in order to follow them, but generally even if you do so for bulge lenses, it's harder. So what's the solution? The solution is satellite parallax. And just as a reminder, what is satellite parallax is when you observe the same microlensing event from two distant observers or more, you will get two different light curves. And by measuring the offset of this light curve, both of time and peak magnification, you can derive very accurate microlensing parallaxes down to the small parallaxes that you expect for bulge lenses. So we are running this Spitzer campaign for the last 5 years, and we're looking forward for our final year in 2019. A few highlights in our 2018 season. First of all, as Andy mentioned, for the first time we actually have KMT alerts. It's important to understand this is a follow-up survey. We do not detect microlensing events. We follow microlensing events that were detected by other groups, and the KMT alerts actually contributed a significant fraction of our microlensing 2018 events. In addition, we have KMT real-time data for OGLE and MOA alerts, and this is very important for our selection process. And lastly, we have, for the second year in a row, a dedicated LCO follow-up program for specific Spitzer microlensing event that Wei Cheng will mention later today. Surprisingly, additionally, we had two special events that were not discovered by the normal traditional microlensing surveys, one by Assassin and one by Gaia, and actually the Gaia event was later also followed in the fall, part of different and a wider program with Spitzer to follow Gaia microlensing events. But I won't go into details for these two. Now, the key thing to derive statistical conclusions is to have unbiased sample and to have a control sample that you can compare your planetary signals. And for that, in 2015, in Jennifer Yee's paper, we developed very strict selection protocols in order to detect our events and to minimize the bias. And we have several ways to detect them, objectively, subjectively. And I'll go with some example about that, but we do have several biases. The key thing that these biases are not affected by planets, or they are not planetary bias, they are somehow bias our sample compared to maybe a general microlensing sample. First of which, because this is a follow-up mission, by the time that we select an event until first observation, we have a time lag of between 3 to 10 days, so we are biased against short timescale events. The second thing is that what we require to be included in our sample, we need to have what we call good parallax measurement that later in Wei Zhu's paper in 2017 we better defined in a more quantitative criteria. But to understand, we need to have some signal in Spitzer light curve. We need to have some slope, some magnification change, and therefore events that will peak much earlier in Spitzer, by the time that we observe them, they might go back to a baseline, and so we will not include them in our sample. But again, those two biases are not affected by the presence of the planet, so it's fine. Now, just to give you intuition about our selection process, I will go through the 5 planetary events that we followed in 2018 and see how they fall in our selection protocols. So the first event is actually an event that had a planetary anomaly very early in the season, a month before our first upload. So you can ask yourself, how can it be part of an objective sample? Well, exactly for this, we developed our objective criteria. By the time of the first upload, the change in magnification change in brightness compared to the baseline was such that it followed our objective criteria, so it is part of the sample. The second thing that we need to see is that we actually have Spitzer signal, and we do. So this is an example of an event that is part of our sample. The second example is of another event with an early anomaly, this time even earlier, like 2 months before our selection. This event is what we call falling event. So by the time that we can select it, it's already after peak. And so what we require is to have expected change in magnification during the Spitzer season of at least 0.3 magnification, delta magnification. According to the single lens model, when you take out the planet, it has only 0.29. So it's at the border of meeting our criteria, and we need to really assess that it's not part of the sample, but I think that it won't be at the end, although we do have a nice Spitzer signal. The next example is of an event that we selected subjectively when it was still rising, and for this event we can only count planets that will be found after our selection. And we actually selected it with a condition, what we called subjective condition, that it needs to meet some brightness threshold at a certain time, actually just after a planetary signal, but the margin is large, so so it is part of the sample, and we have a very nice Spitzer signal, so again, part of our sample. The next one, another subjective example, selected before peak. Just after peak, there is a nice planetary anomaly. But when you look at the Spitzer signal, you have a very, very shallow slope below anything that we published today. So we still need to see if this slope can pass the criteria that we set for good parallax measurement. But I will go back to this event later. The last event is an event that actually the announcement of the event was after the anomaly and immediately falls after, so it's not part of a sample, and we do not have a good signal in Spitzer. So in summary, over the last 5 years, we followed 763 microlensing events. However, out of these, only or just 507 microlensing events were both meeting our selection criteria and have some good signal in Spitzer. So this sets our control sample. The first thing to do is to analyze single-lens events and to see two things. First of all, to see that we can actually detect microlensing parallax of bulge instance, and we can. And the second thing is to derive the distribution function of the underlying population that we can compare our planets later. The next thing that we need to do is also to take into account the planet sensitivity of each individual light curves. And when we did that, or Wei Zhu actually did that, what we found out that if you have equal frequency of bulge and disk planets, you expect to detect 2 disk planets for every bulge planet that you detect. And if we look at the planets that we detected so far, so we have 6 published planets. However, one of them is excluded from the sample, and we have additional 4 with clear signal. And if you look at them on a galactic distribution plot, you can see that from the 5 published ones with that are part of the sample, we have 3 in the disk and 2 in the bulge. And I told you that we are expecting 2 to 1. So still not a very strong statistical conclusion. The only thing that we can maybe derive of that there is no strong deficit of bulge planets that some prior Bayesian estimates suggested for that. So we are looking for 2019 season, and we hope that in 2019 we can get more planets. But there is another question: can we actually exploit more from our current data? So about I think a month ago, maybe exactly a month ago, Andy noticed that in 2018 we followed 2 events that are very close to each other, only 1.5 arc minute away. So we actually have data for the other event in the light curve of the other event that we followed, and this led to even larger survey to actually detect: do we have many of these examples? And yes, we do. So we have for 29 events, we actually have data for 29 Spitzer events. We have data while the event was actually magnified in another field, but we also have for 80 events baseline, and these baselines can be very important when you try to see if your slope is real or not. And we have 103 other events that were not selected by Spitzer, but happen to peak within our stamps. They might be too faint, so we actually need now to go for each of them to see if we have a signal. But these include 2 or 3 additional planetary events and short timescale events that we couldn't do otherwise. But by chance, or by these Latin words that only Sebastiano and Andy can say, we happen to follow them. Can we do more? Well, yes. Every time that you observe the 3.6 micron image with Spitzer, you also get a 4.5 micron image. So the signal is expected to be somehow weaker, but we now need to go and see if we can actually detect more there. And again, within this footprint, we have a few new Spitzer events and specifically a few additional planetary and short timescale events. We hope that we can actually extract the data. Just to show you the potential of this, I will go to one example of the event that we have baseline data. So I told you that this is a planetary event from 2018 that meets our selection criteria, but we are not sure that we have a signal in Spitzer. It happened to be that this event was also observed in 2 other seasons. And when you look at the light curve of those 2 other seasons, they are quite flat. And this is raw data. It's before Sebastiano's fancy work, which we think that can actually make the scatter here shallower. And we hope, still, it's work in progress. I'm not sure that we can put it in our sample, but it's give us good hopes. And I will end with that, and happy to get questions. Thank you.